asking for help with identifying the correct sketch of a compound in aqueous solution. Identifying the correct sketch of a compound in aqueous solution. So before we get to the topic itself, let me remind you what's going on here. If we have an ionic compound, we have a metal and a nonmetal, right? If we have a metal and a nonmetal and it's aqueous, then what that means is if it's aqueous with a metal and a nonmetal, that's an ionic compound. What that means is in solution, it's really a metal plus and a nonmetal minus, right? You guys remember those symbols there? That's what aqueous actually means, right? That they're dissolved, that they're broken up. Now, if it's a covalent compound, let's say like glucose, which is C6H12O6. If this is aqueous, then it doesn't break up because there's no metals here, right? So this is actually going to be in solution as C6H12O6, right? So if it's molecular, it's going to look like this. If it's ionic, it's going to break up when it gets into solution. Okay, so what that's going to look like when it's in solution, what does the aqueous actually mean? Aqueous actually means that we have some ion, well, I'll take the positive ion for now, and we have water molecules which are surrounding it. Now remember that oxygen is actually electronegative, so it's partially positive, it's partially negative, right? So the oxygens are going to be closer to that. You're going to have a bunch of water molecules surrounding this, and you're going to have the nonmetal, which is something, I don't know what NM stands for, right? But it's going to be something that looks like this, right? And the orientation of the water molecules is probably not the most important thing here, but just be advised that the water molecules will surround it. And if it's glucose or some sort of molecular compound, it's just going to be, you know, big globular compound with water molecules all around it, okay? So having that in mind, those are horrible water molecules, but let's go back over to the question now and look at it. Yeah, I'm still here. All right, so imagine a small amount of each compound in the table below is dissolved in water. Pick the sketch that best describes the solution, what it looked like at an atomic level. So before I look at it, I'm actually going to make a prediction. Calcium chloride. So let me come over here. Let's go to a new layer. Let's get rid of that layer. And let's say calcium chloride in aqueous solution is really, right, calcium 2 plus aqueous plus a bunch of chlorides. Aqueous is actually two of them, right? So what this is going to look like, it's going to look like a calcium and two of these guys, right? So let's color these because maybe in our sketches that we colored, and so there's going to be, let's suppose that chlorines are red and that calciums are green. There's going to be one, well, anyway, you know what I'm doing here. We get a green here. So this is our calcium. There's going to be a bunch of water molecules around this guy and a bunch of water molecules around this guy. And they're going to be broken up 1 to 2, right? Because there's two chlorines for every one calcium. So now that I've got a prediction in my head, I'm going to go look at it, and I'm going to find one that looks like that. All right, this doesn't look like that because it's not broken up, but they are 2 to 1. You see that? Maybe those are the chlorides and the calcium is in the middle, right? All right, so let's go here. Well, this is not it because, well, I don't know. What is 3 to 1? We have no 3 to 1 here, so this makes no sense. Okay, this is not it because these are looks like maybe chlorine molecules. Okay, this is for the person who thinks this is a chlorine molecule, right? But it's not. It's chlorine ions that come off. Let me go back over to my sketch. Right, it's going to be 2 chlorines for every 1 calcium, and they're not going to be bonded together, right? So this is not it. What about this one? No, this is not it because they're 1 to 1, right? So there's two of the blue and 2 yellow. That's not 1 to 2. It's 2 to 2, right? All right. So this is not it because what's green? If these are yellow, who knows? I don't know what that's about. All right. This is not it because these are molecules, right? So I'm starting to get a little nervous here. All right, maybe this is it. So I've got 1 blue and 2 yellows and 1 blue and 2 yellows. This is definitely it, right? See, I've got if these are chlorines, and we're not told that they're chlorines, but they can be, right? If these are chlorines and that's a calcium, then there's 2 chlorines or 2 chlorides, right, for every calcium ion in solution. And there's a bunch of water molecules all around it, right? So it's definitely that. Let's look and see what's wrong with number 8. Because it can't be 2 of them that are correct. Right, what's green? Right, where's that come from? We don't know. So this is definitely not right. So it's definitely 7. Let's do magnesium chloride. And oops, this is going to be the same thing, right? Because there's 1 magnesium for every 2 chlorides. Let's come back over here. Let's make a new layer. I'm going to predict every time. I don't want to guess, right? Let's go with red. Let's go with black. Magnesium chloride in aqueous solution means, it really means, the aqueous means that the magnesium and the chlorides are broken up. And magnesium's in group 2, so it's going to be 2 plus. And the chlorides are in group 7, so it's going to be 1 minus. There's going to be 2 of those for every 1 magnesium, right? 2 of those, and they're going to be also surrounded by water molecules. Okay, so really what we're going to have here again, let's choose a blue ball for magnesium this time. And let's choose green balls for chloride. So there's going to be 2 chlorides for every 1 magnesium. It's going to be a 2-to-1 ratio. So let's find a 2-to-1 ratio. All right, again, not a 2-to-1 ratio. That's not going to work. No, what's that? Who knows what that is? We don't have a 2-to-1 ratio there. It's a 3-to-1 ratio. And what's the green? We don't know. All right, so this is a 2-to-1 ratio, but the yellows look like they're bonded to each other. So we don't have any molecules in there. All right, this is a 2-to-2 ratio. That's not correct. Okay, what's the green again? We don't know, right? That makes no sense. All right, so these are molecules again. That's not going to make any sense. Son of a gun. Same picture. This is a coincidence, all right? This is a coincidence, but that's it. All right? And again, we got a green here, which doesn't mean anything, okay? So this may bother you that exactly the same picture, but remember, in our predictions, we knew it was going to be a 2-to-1 ratio for both of them. Why? Because they're both in group 2, right? Let's check that. We're going to get that right, and boom. I'm going to pull one more up here and see if we get a hard one. I know, yeah, oh, there you go. There's one. It's carbon monoxide. This is not a molecule, right? I mean, this is not ionic because there's no metals in that. So let's come over here. I'm glad I did that. Don't save that. Let's go over here now and say carbon monoxide, aqueous, is not going to break up because there's no metals in it. This is not ionic. So it's really going to look like this. Carbon, it's really a triple bond, I guess, right? Surrounded by a bunch of water molecules. All right. So, and they're going to be 2 different colors. So let's suppose one is blue and one is green. That's what we're looking for. We're looking for a diatomic molecule. A diatomic molecule surrounded by water molecules. Let's go here. And we're going to go, no, that's not diatomic. No, that's not, those are ions. Those are broken up, right? Oh, there it is. That's the diatomic, right? That's it. It's number 3. These are not diatomic because they're broken up, right? These are not diatomic because there's 3 different kinds of atoms here. These are diatomic, but they're elemental because both those atoms are the same thing. So that's not it. This is a 1-to-3 ratio, and it's not a molecule. And here's a molecule over here, but what are these, right? We don't know what those are. So we're going to know it's number 3. Now, VCl3. Okay, what's that? Well, VCl3, you have a metal, right? And you have a non-metal. So this is definitely going to be broken up into a vanadium, 3 plus ion, and 3 chlorines. Let's choose a different color for those now. So we're excuse me, please. We're going to see an ion that's broken up 1-to-3. That's what we're going to see here. So you see, I'm predicting in advance. So it really is way different kind of a question if I predict in advance. So this is 1-to-3, but this is a molecule, and this is not molecular because it's ionic, right? So this is not 1-to-3, it's 1-to-1-to-3. That's not correct. 1-to-2. This is a 2-to-2, right? So this is not the 1-to-3 I'm looking for. This is not a 1-to-3 I'm looking for. This is not the 1-to-3 I'm looking for. Aha! There's the 1-to-3 I'm looking for. It's number 7, I'm sure of it. And that's also not 1-to-3. This is number 7. So we got a couple different examples here. I've got a student waiting for me, so I'm going to cut this video off. And I am going to post this and send the link out to the class. Good luck. Good luck, students. I hope this ends up being an easy topic for you.